Okay, today we'll be doing section 4.1, angles and triangles. I'm going to start off by classifying triangles by their angles. So each triangle has two names, one based off the angles they have, and the other will be based off their sides. So we're going to start with the angles first. An acute triangle is a triangle with three acute angles. An obtuse triangle will be a triangle with exactly one obtuse triangle or obtuse angle. And that's because if I had more than one obtuse angle, they would have to be over 90. So 91 and 91 would be very small ones, and that's already 182, which would be over the limit of our maximum 180 degrees for a triangle. On a right triangle, it's going to be a triangle with exactly one right angle. For the same reason, if I had two right angles, I would be at exactly 180, but it would still not leave me any room for my third angle measure. And finally, an equal angular triangle is a triangle with exactly, with three congruent angles. And since we know that all the measures of a triangle have to add up to 180, we could also see that each angle is going to be equal to 60 degrees then. As you can see, an equal angular triangle could also be considered an acute triangle as well, because all of those three angles are less than 90. Now moving on to classifying the triangles by their sides. So I'm going to start with a scalene triangle, and this is going to be a triangle with no sides congruent. And then we're going to have an isosceles triangle, which is going to be a triangle with two sides congruent. And then we have the equilateral triangle. This is going to be a triangle with three congruent sides. So again, each triangle will have two vocabs to be associated. I could have a right scalene triangle. I could have an acute isosceles triangle. I could have an obtuse isosceles triangle. So they each have their own name based off their side and their angle descriptions. In examples 1, 2, and 3, they want us to identify whether it's acute, equiangular, obtuse, or right. So I'm going to go ahead and highlight these. ABD would be this triangle right here. A, B, D. And that is going to be, I see all the 60 degrees in there. That means they're all congruent. I'm going to call this an equiangular triangle. And also, because it is also all less than 90, I could also call it acute as well. Then we're moving on to 2, and we're looking at BDC. So BDC is going to be this triangle way over here on the right. And immediately I see the 120 degrees up there in the top corner, which indicates that this will be an obtuse triangle. Then finally, let's go look at ABC. ABC is this outside one. ABC. And if I grab these angles together down here, those are going to add up to 90, which is going to tell me ABC is going to be a right triangle. Moving on now to 4 and 5. They gave us a little bit more information in the directions. They tell me C is the midpoint of BD. So I'm going to go look at BD right now. If C is the midpoint here, then that would tell me that C or CD is also going to be 4. Also in the information we see that E is also the midpoint of DF. So I'm going to go ahead and put a 5 up top here to show that E is in the middle. And then the last thing I notice is in the diagram itself, it shows me if I have one marking that it's going to be 8. So I'm going to go transfer the 8 over on that side as well. And now I'm going to go and identify number 4 wants ABD. So ABD is right here. And I see the 8s and the 8s, so I'm thinking isosceles, but then when I notice down here on the bottom, 4 plus 4 is also 8, indicating that this is going to be an equilateral triangle. And put equilateral. Moving on to ABC. That's going to be this one out here, A, B, C. I have an 8 and a 4, so those are not congruent. And then the markings that have 1 and double down here shows that all of them are going to be different. So that's going to be a scalene triangle. On number 6, I noticed due to the markings here, we have a scalene triangle, which is helpful because I can set those algebra equations, expressions equal to each other. So I'm going to say 3x minus 4 equals 2x plus 7. I can solve for x now. Subtract that 2x to the other side. And I get x minus 4 equals 7. Adding that 4 over to the other side, I get x equals 11. So that was the first thing they wanted me to do, was find x, and I did that right here. But they also want me to find the measure of the unknown sides as well. So LM is 17. We can already see that. I'm just going to write it up there. And then we have LN, which is going to be 3 times the 11 we just found, minus the 4, which is going to be 33 minus 4, which is 29. And then because I already know that those two sides are congruent for LN and NM, I can go ahead and say NM would also have to be 29 as well. And then if you notice from the diagram here, this is a classic example of where the diagram's not drawn to scale. So obviously I have a 29 and a 29. That's not a very good picture for those measurements. On number 7, we have an equilateral triangle, which tells me that FH here, that's 3x or 6x plus 1, would be equal to FG, which is 3x plus 10, also equal to HG at 9x minus 8. They're all equal to each other. I only need to pick 2 of them, so I'm going to go ahead and pick my first 2 to solve. 6x plus 1 equals the 3x plus 10 is the one I'm going to choose. Go ahead and subtract the 3x. And I get 3x plus 1 equals 10. Subtract 1. And I'm going to write it over here. 3x equals 9. Divide by 3. X equals 3. So again, I found the x just like they asked for. Here's my first answer. And then I had to find the unknown measurements. This time I only have to take one of them because I know once I do one algebra, I can go ahead and say all of them will be the same amount. 3 is not working. My pen's not working very well today. That's a 3. Okay. So that's 18 plus 1, which is going to be 19. So now I can say FH equals 19, which means FG is also going to be 19. And finally, HG will be 19 since it's equilateral. They all have to be the same amount. On number 8, we have triangle MNP is an isosceles triangle with MN congruent to segment NP. So the first thing I'm going to do is draw a triangle. I like to have a sketch. Again, you don't need it to be drawn necessarily to scale, but I'm just going to go ahead and say MNP. What you do need to do is mark the correct segments congruent so that we can see that. Segment MN is congruent to segment NP there. And now I'm going to go and look at the rest of the instructions. It says MN is 2 less than 5 times X. So I am going to write this as MN is 2 less than 5 times X. So since I'm taking away the 2, I have to have the negative with the 2, and I put it at the back. Then it says NP here. NP is 7 more than 2 times X. So I'm going to say NP equals 7 more than 2 times X. So I'm going to put 2x plus 7 more. So making some algebra there. And then finally, PM is going to be 2 more than 3 times X. Okay, and then I gotta use some algebra to solve this. So I'm gonna go back and pick out the 2 segments that were congruent, which would be MN, this one here, and NP, this one here. So I'm going to go over here and say 5x minus 2 is equal to 2x plus 7. Since those are the isosceles congruent sides, let's go ahead and move that 2x to the left. And I get 3x minus 2 equals 7. Let's go add the 2 to the other side. 3x equals 9. Divide by 3. And then x equals 3. And again, this was part of the directions that said first find x and then go find the missing side. So I'm going to go start over here and I'm going to say mn, and we said that it was going to be 5 times that 3 minus the 2, which is going to give me 15 minus 2, which is 13. That's my first one. And then my second one here will be NP. And that's going to be 2 times 3 plus 7, which is 6 plus 7. And that's also 13, which it should be because we already knew that that was going to be congruent. And then the final one I'm going to do is going to be PM. And that's going to be 3 times 3 plus 2, which is 9 plus 2. So therefore it's 11. So there are all my unknown sides right there. Now, the theorems we're going to talk about, the first one is something you're already familiar with. It says the sum of the measures of all 3 angles of a triangle is equal to 180 degrees. Go ahead and write that out. Use any symbols or notation that might shorten it up for you. That's fine. As far as our definitions, we have exterior angles, and this is going to be an angle that forms a linear pair with an angle inside a triangle. And as you can see, I have a diagram right there, so go ahead and write that up, and then we will identify which one is our exterior angle and which one is our interior angle. So for this, we have example. I'm going to say angle 1 is an exterior angle. So that would leave angles 2, 3, and 4 as all being interior angles. Remote interior angles are going to be the two interior angles that are not adjacent to the exterior angle. So as I mentioned earlier, 2, 3, and 4 are all interior angles, but remote means far away. So we're going to say 3 and 4 are going to be the remote interior angles to angle 1 because they are not adjacent to angle 1. So I'm going to say example, angle 3 and 4 are remote interior angles. Our second theorem, theorem 4.2, is going to say the measure of an exterior angle is equal to the sum of the measures of the two remote interior angles. So go ahead and write that out, and then I'll draw a diagram to explain it. So let's go ahead and draw a diagram that we saw on that last slide that looked like this, where there was an angle 1, and then we had angle 2, angle 3 here, and angle 4. So this theorem is telling us that measure of angle 1 is equal to the measure of angle 3 plus the measure of angle 4. Okay, which should make sense, and here's why. If I have angle 1 and 2, that should be a linear pair that adds up to 180. Now if I look at angles 3 and 4, if I put those together along with that same angle 2, they also add up to 180, but because they are inside a triangle. So this is why this theorem works out. And so now we can always say the exterior angle is equal to the sum of the two remote interior angles. Corollary is a new vocab word that just really means a fancy word for a special theorem. It's a theorem that follows as a direct result of another theorem. So go ahead and write that out. Corollary 4.1 says the acute angles of a right triangle are complementary. And this is true because if I already used up 90 degrees for my triangle, I have 90 degrees left over for the other two angles. And since they add up to 90, that's going to be called complementary. And then corollary 4.2 says there can be at most one right angle or one obtuse angle in a triangle. And we had already discussed this at the beginning of our notes, and this all comes from that one theorem that says all three angles add up to 180. So they are called corollaries because we can conclude more information based off that one theorem. Okay, for my last examples, it says we are going to find these numbered measured angles, and so I'm going to go ahead and look. On number 9, I can actually start on either triangle, and don't forget, we know that all angles of a triangle add up to 180, so I'm going to go look at this bottom triangle here. Let me do a highlighter, it works a little better. So we're going to say measure of angle 3 plus 23 degrees plus 24 degrees should all add up to 180 degrees for my triangle. So far I have measure of angle 3 plus the 47 that I know of equals 180. I can go ahead and subtract that 47 on both sides, and I get 133, it looks like. So measure of angle 3 will be 133 degrees. My pen is just acting up really bad. Okay, so that was for the lower triangle. Let's go move to the top triangle on the right here. I can say angle 1 and angle 2 are congruent, as I can see in the diagram. So I'm just going to label them as x, since I know they're going to be the same amount. And I am going to go ahead and say 2x plus that 105 we see over there is going to add up to my 180 degrees for the triangle. Subtract the 105, and I get 2x equals 75. It's going to look like it's going to give us a decimal. X equals 37.5. So both angle 1 and angle 2 are the same. So I'm just going to go ahead and write them out as 37.5 for each of them. So those are all the 3 angles I was looking for on number 9. Over here on number 10, I can go ahead and start with the top triangle because I can see I have a right angle up in that top corner. So you always have to have at least 2 angle measures or known that they are congruent to begin a problem. And I have 2 angle measures. I have the 90 plus the 31 plus the measure of angle 2 equals 180 degrees. So far I have used 121, and now I'm going to subtract that 121, which tells me that angle 2 is going to be 59. Oops, angle 2. Now that I know angle 2 is 59, it's a vertical angle with angle 1, so I can put the 59 right there for angle 1 and say 59 plus 22 plus angle 3 equals to 180 for that lower triangle. So far I have used 81 degrees. So 81 along with angle 3 should add up to 180. Let's go subtract that 81. And I get angle 3 equals 99. So there are the missing angles for number 10. On number 11, we had a theorem that said the exterior angle, which is angle 1, is equal to the measure of the two remote interior angles, and those are identified as 27 degrees and 52. So this will be easy if we remember that theorem. Measure of angle 1 will be 79 degrees. If you didn't remember that theorem, you could always find out what this angle down here was going to be and then subtract it from 180 since they are a linear pair. My exterior angle theorem just is a shortcut. So again, let's practice using our new theorems. Measure of angle 3 then is equal to 43 degrees plus the 22, and so that's going to give me a total of 65. And then we are done with our notes for today, so as always, ask me questions when you see me again.